Welcome to the Deep Dive, the place where we cut through the noise and get straight to the strategic core of today's most complex technologies.
Thanks for having me.
So if you're involved in building the next generation of intelligent systems, you definitely know the central challenge, maybe the most frustrating challenge.
Oh, yeah.
Every device at the intelligent edge, could be critical factory equipment, a next-gen smart camera, maybe a specialized automation drone. It needs real-time processing, high speed, low latency.
And it's not just simple processing anymore, is it? We're talking dynamic AI workloads, pretty sophisticated control loops, complex sensor fusion, things that traditional fixed hardware, your standard CPUs, or even ASICs, they just struggle with.
They really do, especially with the power efficiency constraints.
Exactly. So the demand for localized adaptive acceleration, right where the data's coming in, it's absolutely urgent now.
That's the landscape we're diving into today. Our mission is to take a really exhaustive look at the AMD Kria portfolio of adaptive system on modules, or SOMs.
And this isn't just, another chip announcement. It feels like a pretty radical shift in how embedded systems get engineered and financed, actually.
Totally. We want to uncover exactly how this tech kind of changes the rules, how it bypasses those traditional, really high-stakes barriers to hardware acceleration.
And how it profoundly changes the economics of embedded design for you, the developer, or maybe the business leader, making those big strategic decisions.
We've pulled together a deep stack sources for this one, everything from detailed technical white paper.
Yeah, showing the nitty-gritty on the K26 versus the K24 hardware.
Right, to the strategic thinking behind this big software paradigm shift they're pushing.
And crucially, some pretty eye-opening analysis on total cost of ownership, TCO, which, let's be honest, often gets missed when people just look at the sticker price.
That's a great point. Okay, let's unpack this then.
Wow.
Starting with the fundamental idea, adaptive computing at the edge, and why a system on module, a SOM, is the vehicle for this change.
Okay, so the why now, I think we've really hit a tipping point. It's driven by, two main forces.
Which are?
First, just the sheer explosion of intelligent edge computing. It's everywhere. Industrial consumer markets.
You can't avoid it.
Pretty much. And second, the increasing complexity of the data pouring off all these sensors, these new workloads and deep learning inference, high-speed vision processing across multiple channels, guaranteed precision motor control.
Things that need serious horsepower and reliability.
Exactly. They need extreme throughput and deterministic low latency. A delay of just a few milliseconds in a robot arm, that could be a failed process. Or worse, a safety incident.
Yeah, determinism is non-negotiable there, which means you can't just punt the data back to the cloud, right?
Yeah.
Or even to a server rack down the hall sometime.
Absolutely not. The acceleration has to happen right there, localized, on the device itself.
And the Kria approach, it seems to tackle that head on, leveraging these adaptive sockets to accelerate the whole pipeline.
That's the key. It's not just accelerating one bit, like the AI math in a fixed block. It's accelerating everything, from the moment raw sensor data comes in, through all the pre-processing, maybe noise reduction, image enhancement, then the actual AI inference.
And then actually controlling the output.
And finally, directly controlling the system output. Yeah, it's a full stack, totally customized acceleration pathway you can build.
Wow. And that capability is built on the Zinc UltraScale plus MPSoC core. That's the heart of Kria.
That's the foundation. It gives you what we call 3 degrees of freedom. And this is really fundamental to genuine adaptability.
Okay, let's break down those degrees of freedom, because that sounds like the core technical differentiator here.
Right. So first, you've got the standard software programmability that comes from the embedded ARM CPUs, your traditional software world running Linux applications.
Familiar territory for most developers.
Exactly. Second, you have the specialized hardware programmability. That's the FPGA fabric, the programmable logic, or PL. This lets you literally create custom hardware accelerators, tailored precisely to your application's algorithm or maybe even its physics.
Down to the microsecond level kind of timing.
Yeah, really fine-grained control, allowing for that deep customization.
And the third degree, you mentioned scaling and partitioning.
Precisely. It's the ability to easily scale and partition those tasks across the different processing elements.
Meaning you can decide where each piece of the job runs best.
That's it. The system designer can assign every single function. Maybe it's an OS task, maybe a network packet routing function, maybe a specific layer in a neural network, to the single optimal computing engine for maximum efficiency.
So unlike a traditional system where you might be stuck running something slow on a CPU.
Right, because you had no other choice. With Kria, if a CPU is the bottleneck, you can potentially move that function into the PL fabric and create a dedicated hardware accelerator just for that specific task. Hashtag tag 1.2, defining the System on Module SOM value proposition.
Okay, that makes sense for why adaptive hardware is needed. Now let's pivot to the form factor itself, the system on module. Why put this powerful adaptive chip on a module? What exactly is a SOM, and why is it more than just, convenient?
Good question. So a SESOM is basically a highly integrated, often credit card-sized circuit board, and it encapsulates the most complex, the highest risk, and frankly, the most expensive parts of a digital system design.
Like the main chip itself.
Yeah, the core compute chip, the MPSO in this case, but also all its critical support systems. We're talking high-speed DDR memory.
Always tricky.
Always tricky.
Yeah.
The critical power sequencing and regulation circuits, non-volatile storage like eMMC or QSPI flash, and often even the initial thermal management components like a heat spreader.
So it's basically the pre-built brain of your product. Fully designed, fully tested.
That's a great way to put it. The brain, ready to go.
Which means the main value for the OEM, the company building the final product, is, it's massive risk mitigation, isn't it? Wiping out a huge chunk of that non-recurring engineering cost, the NRE.
That is absolutely the core value proposition on the engineering side. OEMs get to completely bypass that super high-risk, NRE-heavy phase of designing the high-speed digital core.
Just thinking about routing high-speed DDR4, DDR5, that's a nightmare.
It requires incredibly specialized engineering skills, very expensive simulation software, multiple board revisions usually, just to get the signal integrity right and meet timing. It's painful.
So the SOM vendor, AMD in this case, takes on all that headache.
Exactly. They handle the complex digital design, the signal integrity validation, the power integrity. The OEM's design team, they can focus their precious resources entirely on their own secret sauce, their proprietary application features, the user interface, the sensors, the actuators.
And designing the carrier card, which becomes much simpler.
Much simpler. The carrier card just links the SOM to the outside world power, peripherals, connectors. All the really hard, high-speed stuff is contained on the SOM. And that engineering simplicity, it must translate directly into big economic value on the manufacturing floor, right? You mentioned maybe going from an 8-layer board down to 4 layers. That sounds huge.
It is a gigantic operational win. Think about routing high-speed memory like DDR or PCIe interfaces. You need precisely matched trace lengths, controlled impedance, multiple power and ground planes just to manage noise.
Forces you into complex board designs.
Right. Typically 8, 10, even 12-layer PCBs, which are expensive to make and harder to assemble reliably.
More layers, more cost, more things to go wrong.
Exactly. So if all those high-density ball grid arrays, BGAs, the complex power plans, the high-speed memory routing, if that's all contained and validated within the SOM.
And the OEM's main board, the carrier card, gets way simpler. Often, yes. You can potentially simplify your carrier card down to a much more cost-effective 4-layer, maybe a simple 6-layer design. That cuts unit costs, simplifies manufacturing, boosts yield. It's a fundamental economic lever being pulled.
Okay, so the SOM form factor tackles the hardware complexity and cost.
Yeah.
But you said that's only half the strategy. The other half is about who they're targeting.
Right. Historically, adopting FPGAs, adaptive hardware, it was tough. Hindered by 2 big barriers.
Which were?
One, the specialized knowledge needed. You typically had to know hardware description languages like VHDL or Verilog. It was a niche skill set.
A steep learning curve.
Very steep. And 2, those prohibitive non-recurring engineering costs we just talked about. The upfront investment was huge.
Which basically locked out anyone who wasn't building something really bespoke, high volume, and probably high margin.
Pretty much. So the Kria strategy aims to flip that script entirely by offering this pre-integrated, production-ready module.
The SOM we just discussed.
Yeah. And combining it with a robust Linux-based software ecosystem, plus the Kria App Store, which we definitely need to dig into later.
Okay.
AMD is actively trying to dismantle those old barriers. They're not just selling raw silicon to the traditional hardware engineers anymore. That's still there, but it's not the main focus.
So the focus shifts from just selling chips to providing a whole solution, a complete, accessible, ready-to-go platform.
Exactly. And that dramatically expands the potential user base. They explicitly talk about targeting the millions of software and AI developers out there.
People who probably wouldn't have considered FPGAs before.
Right. People who saw adaptive hardware as too complex, too risky, or just way too expensive to even think about. The SOM becomes the critical bridge. It hides that deep hardware complexity behind a standard Linux interface they already know.
That makes a lot of sense. And the market positioning reflects that pivot too, doesn't it? With the production SOMs versus the starter kits.
Yeah, clearly segmented. You've got the production SOMs, the K26 and K24 families, designed to go directly into end products that ship to customers.
Ready for volume.
And then you have the starter kits. Things like the KV260, the KR260, the KD240. These are plug-and-play development boards designed for super rapid evaluation, proof of concept, application development.
Get started quickly, figure things out, then move to the production SOM.
That's the flow. And this whole product line, it's clearly targeting those high-value, high-growth verticals where, frankly, getting to market fast is everything.
Like Vision AI.
Vision AI is huge, smart retail analytics, industrial machine vision, security, also industrial IoT needing that deterministic control we talked about, sophisticated robotics platforms, precision motor control systems.
Yeah, these are serious markets.
It's a serious play in the embedded world, positioning adaptability as the key competitive edge delivered through a software-friendly approach.
Okay, let's switch gears and look under the hood. Let's get into the engine room. This is where it gets really interesting for me. Digging into the specific chips, how they're set up, how they handle those tough industrial and edge demands. Because the Zinc UltraScale Plus MPCC is the brain here.
Right.
But you described it earlier.
Yeah.
It's almost like a split personality, right? Two distinct domains working together.
That's a pretty good analogy, actually. The Kria SOMs are built around a custom-configured version of that Zinc UltraScale Plus MPCC, and it organizes its compute resources into two tightly integrated domains.
Okay, domain one.
Domain one is the processing system, or PS. Think of this as the traditional software environment. It's got a quad-core ARM Cortex-A53 processor.
Standard ARM cores?
Yep. Running the operating system, typically a standard Linux distro like Ubuntu, handling all the high-level application logic, managing communications, general housekeeping tasks. This is the comfort zone for software developers.
Okay, familiar ground. And domain two.
Domain two is the programmable logic, or KL. That's the adaptive part. That's the FPGA fabric itself. It's basically this massive sea of configurable logic blocks and routing resources.
Like digital clay you can mold.
Exactly. You can wire it up to become almost any custom digital hardware circuit you can imagine.
And the Kria K26, for example, it packs a lot into that PL fabric, doesn't it?
It really does. We're talking significant resources. Over 250,000 system logic cells, those are the fundamental building blocks. Around 1,200 dedicated DSP slices. These are hardened blocks optimized for math-intensive operations like filtering or FFTs.
Crucial for signal processing in AI.
Absolutely. And 64 blocks of UltraRAM, which is fast on-chip memory. These aren't just abstract numbers. These are the actual engines that run your custom accelerators for imaging, for signal processing, for the AI inference. Having plenty of these resources is what lets the chip handle complex applications efficiently.
Now, beyond just the raw compute, security is obviously huge at the edge. Is that just handled in software on the ARM cores?
No, and that's important. Security is integrated right onto the module at the hardware level. The K26 SOM, for instance, includes an embedded security module, specifically an Infineon TPM 2.0, a trusted platform module.
Okay, TPM. What does that enable?
It enables crucial security features like measured boot, secure key storage, and establishing a hardware root of trust within the MPSE itself. For industrial applications, defense, anywhere system integrity is paramount. Having that hardware-enforced trust is often mandatory, not optional.
Makes sense. Now, physically getting all that data on and off this powerful module, connecting it to the carrier card must be a challenge given the speeds involved.
Oh, it's a massive technical challenge. You need specialized connectors. Kria uses a pair of these high-density connectors called Accelerate HD Slim Body Arrays, 240 pins total.
Not just standard headers then.
Definitely not. These are specifically engineered for really superior signal integrity and also ruggedness.
Yeah.
They have to support incredibly high data rates. We're talking up to 56 gigabits per second, PM4 signaling on some variants, even PCIe Gen 5 compatibility is possible.
Wow. So the connection itself is designed not to be the bottleneck.
Exactly. It ensures that the huge data throughput potential of the MPSC isn't choked off right at the interface between the SOM and the carrier card. That problem is basically solved for the OEM before they even start their design. Hashtag 2.2 industrial readiness and segmentation.
Okay, and for industrial use cases, things like ruggedization, dealing with heat, those are always major hurdles in a project. How does Kria address that?
Yeah, thermal management and just general robustness are big project risks. The Kria design tries to mitigate this proactively. They include a pretty robust aluminum thermal heat spreader mounted directly onto the module itself.
Ah, okay. So that provides a known thermal interface.
Exactly. It
Oh.
pre-validates a core part of the thermal solution needed for tough industrial environments, instead of the OEM having to figure out how to pull heat effectively off the raw BGA package of the MTSC, which is
Very tricky. Lots of complex simulation needed.
right. Instead, they just need to attach their final heatsink or cooling solution to this known stable spreader surface on the SOM. It effectively transfers a big chunk of that difficult industrial thermal design challenge back to the supplier, AMD.
That's clever. And the product segmentation clearly reflects this industrial focus too, right? Like the K24 industrial SOM.
Yeah, look at the specs on the K24 Industrial SOM. It's rated for a much wider operating temperature range, -40 degrees C all the way up to plus 100 degrees C junction temp. That's serious.
-40°C. That covers outdoor equipment in cold climates easily.
For sure. And critically, it includes features like ECC memory support, error-correcting code memory.
Why is ECC so important in industrial?
It's about data integrity and reliability over long periods in potentially harsh environments. ECC can detect and correct single-bit memory errors caused by radiation or other factors. For something like a remote pipeline sensor or a critical robotics controller, you absolutely need that guaranteed data integrity and system uptime. It's often mandated by safety regulations or just required for long-term maintenance schedules.
And you compare that to the starter kit version.
Right. The KD240 drives starter kit. It's meant for a lab environment, right? So it operates from 0 degrees C to maybe 35 degrees C ambient, and it doesn't have ECC. That specific ruggedization and feature set on the K24 Industrial SOM is what ensures it can have a long, stable life cycle out in the field.
So if we zoom out and look at the whole portfolio segmentation, the Kria K26 SOM seems like the workhorse, the powerhouse, targeting more complex applications, heavily focused on vision AI, general robotics, machine learning, needing maximum throughput.
That's a good summary. A K26 is for mid-range complexity and high-throughput needs, whereas the Kria K24 SOM is positioned as the more cost-optimized, power-efficient option.
Lower power, maybe lower cost?
Yeah, designed specifically for more DSP-intensive tasks. Think precision motor control industrial drives, maybe lower-power smart IoT gateways.
And its starter kit reflects that focus.
Exactly. The KD240 Drive's starter kit even offers native Python support.
That's interesting because it aims to lower the barrier for control system architects who might be more comfortable in Python or MATLAB Simulink than traditional embedded C or hardware languages.
Now, we should probably address the elephant in the room here. AMD also makes the Versal AC-Cap platform, which is, state-of-the-art, incredibly powerful.
Phenomenal chips, yeah.
With advanced features like the integrated network on chip, the no-C, dedicated fixed AI engines, targeting really high-performance stuff in data centers, high-speed networking.
Right, so the question becomes, if AMD wanted the absolute maximum performance for Kria, why didn't they just use a Versal chip? Why stick with the Zinc UltraScale plus MPSC?
And the answer seems to be, it was a deliberate strategic choice, right? Not just a technical limitation.
Absolutely fascinating, and yes, deeply strategic. They consciously seem to have prioritized cost-effectiveness, accessibility, and ensuring broad adoption over hitting the absolute peak theoretical performance numbers you might get with Versal. And the Zinc US Plus architecture.
Yeah.
It's mature, isn't it? It's been around.
Very mature. It's been out in the field for, over a decade now? And that history, that maturity, is actually a huge advantage for this market segment.
How so?
Well, it means the US Plus ecosystem is incredibly well established. There's a robust support community online, tons of documentation. The tool flows are stable and well understood.
A big knowledge base already exists.
Exactly. And a massive base of engineers are already familiar with the architecture. All of that minimizes the long-term support risks for the OEMs adopting Kria. And crucially, it dramatically lowers the initial learning curve. That's key if you want to attract those millions of software developers we talked about.
It makes sense. Easier to get started. And maturity usually translates into a better price point, too.
Precisely. The US Plus architecture is substantially lower cost than the leading-edge Versal chips. By building Kria SOMs around this proven cost-effective core, AMD can offer the production SOMs at a functional cost.
Meaning the cost of the whole working module, not just the chip.
Right. The functional cost of the SOM is often estimated to be somewhere between 2x and maybe even 10x cheaper than if an OEM tried to buy the naked MPSoC chip itself and then engineer all the supporting circuitry, the DDR, the power, the board themselves from scratch.
Wow, that's a big difference.
It is. For this massive, volume-driven, mid-range edge market Kria is targeting, accessibility and a competitive price point are often the make-or-break factors for success. More so, perhaps, than having the absolute bleeding-edge performance specs.
Okay, so we've got this mature, adaptable Zinc US Plus architecture on a convenient, cost-effective SOM. Now let's connect that back to the big driver, Edge AI. What does this adaptive hardware actually do for AI performance? Because let's face it, if you're deploying Kria, you're probably chasing really fast, really efficient inference results for models like YOLO, ResNet, things like that.
Absolutely. The cornerstone of Kria's AI capability is something called the Deep Learning Processor Unit, or DPU.
The DP.
Yeah. And it's not just a generic accelerator block. It is a dedicated but also configurable computation engine designed specifically for speeding up convolutional neural networks, CNNs, which are the backbone of most modern computer vision AI.
Okay, dedicated and configurable. Now, critically, you mentioned earlier, it's implemented as soft IP within the FPGA fabric, the PL, unlike, say, the fixed AI engines in Versal. Why is that soft IP detail such a big deal?
It's a fundamental technical differentiator, really. Being soft IP means the designer, using the development tools like Vitis AI, gets to choose exactly how the DPU is configured for their specific needs.
What kind of choices?
They can decide things like how many parallel processing cores does the DPU have, what numerical precision or bit width do those cores use, like INT8, how are these cores interconnected. They can basically tailor the DPU architecture.
To optimize the trade-off.
Exactly. Optimize the trade-off between power consumption, how much silicon area it uses up in the PL fabric, and the resulting AI performance for their specific neural network model and their specific latency budget.
Whereas a fixed, hardened AI engine, once it's manufactured, it's, well, fixed. You get what you get.
Right. A fixed engine might offer higher peak performance on paper for certain operations, but it lacks that flexibility. The DPU, being soft IP, can be adapted and optimized.
So it offers configurability, maybe not always the absolute max theoretical TOPS of a hard block, but tailored efficiency.
That's the idea. And this allows the Kria platform to efficiently support a really wide range of popular neural network architectures, things like VGG, ResNet, YOLO for object detection, SSD, MobileNet for efficient models. You can optimize their execution based on the user's specific constraints.
And how does it integrate with the rest of the system? It doesn't run in isolation, right?
No, it relies on that heterogeneous computing model we talked about. The PS, the ARM processor system running Linux, handles the overall coordination. It manages loading the compiled AI model into the DPU, streams the input data, like video frames, to it, manages interrupts, and collects the results. It ensures the right data hits the DPU at the right time for processing. Hashtag 3.2 performance, and the critical power efficiency story.
Okay, let's talk numbers then. The platform's big promise is delivering AI at half the power with low latency. The K26 SOM, for instance, is quoted as delivering up to 1.4 TOPS trillions of operations per second of AI compute, which sounds pretty solid for an edge device, especially one that might need passive cooling or run off battery power.
It's a respectable number for this class of device, but honestly, the raw TOPS number isn't the whole story here. At the edge, it's really the efficiency that matters most, the performance per watt.
Right. How much compute you get for every watt of power you burn.
Exactly. And that performance per watt ratio, that's where Kria aims to shine. Take one common DPU configuration, the B313S6. The specs show it achieves about 0.92 TOPS.
Okay, just under 1 POPS.
At an estimated overall board power consumption of only 7.9 watts.
Wow, under 8 watts for the whole module running near TOPS AI. That's impressive.
It's a phenomenal number when you think about designing, say, hundreds or thousands of smart cameras or edge sensors that have to be passively cooled, or maybe run off power over Ethernet, PoE, which has strict power limits. 7 or 8 watts for high-speed AI inference, that opens up a lot of possibilities.
And this isn't just theoretical efficiency, right? It translates into real-world capabilities.
It does seem to. We've seen reports and projects, for example, using the KR260 robotics starter kit, where people have successfully run pretty complex object detection models like YOLO X in real time.
Getting decent frame rates.
Yeah, achieving robust performance, maybe in the range of 15 to 20 frames per second, which is often perfectly adequate for many common robotic vision tasks or autonomous navigation functions.
Okay. But you mentioned earlier, thinking about the bigger picture, this superior performance per watt isn't just because the DPU core itself is efficient.
Yeah.
It's about the whole system working together.
That's a crucial insight. The efficiency comes from the tight holistic integration of the entire data processing pipeline within the Zinc MPSE.
Meaning?
Meaning you're not just accelerating the DPU, you can also accelerate other critical functions alongside the DPU using the PL fabric. Things like the image sensor processor, ISP, handling tasks like demosaicing, noise reduction, white balance right from the camera sensor, or other pre-processing logic specific to your application.
And doing all of that within the PL fabric, close to the DPU, that avoids bottlenecks.
Precisely. It drastically minimizes the need to move large amounts of data, like raw video frames, back and forth over slower, higher latency external memory buses like DDR. Keeping the data path short and fast within the chip's fabric is key.
Ah, so that's the optimized sensor-to-image architecture concept again.
Exactly. And the benefits are twofold. One, you preserve image quality. You might avoid lossy compression steps. You prevent visual artifacts like motion blur that can happen with processing delays. And two, critically, you reduce the overall system latency. For safety-critical applications like remotely controlling machinery based on camera feedback, minimizing that end-to-end latency is absolutely paramount.
So it's not just about accelerating the AI math block, it's about accelerating the entire system flow, from sensor input to actionable output efficiently.
That's the power of the adaptive platform approach.
This feels like a good transition point. We've talked hardware, we've talked performance, but arguably the most strategic part of the whole Kria initiative is the software story. Because if this platform is genuinely going to be adopted by those millions of software and AI developers, the interface, the experience, it absolutely cannot feel like traditional low-level hardware engineering. It has to feel familiar. It has to feel like, well, like Linux.
You've hit the nail on the head. The core goal here is, frankly, pretty revolutionary for this space. Enable software developers, people writing Python, C++, Ray, using standard frameworks to achieve significant hardware acceleration and product differentiation.
Without needing to become FPGA experts.
Exactly. Solely by working at the software layer. Eliminating that historical requirement for specialized VHDL Verilog programming expertise. That's the big ambition. Hashtag 4.1, the low-code paradigm, and the Kria App Store.
And the primary delivery mechanism for making this low-code, software-first paradigm actually work seems to be the Kria App Store.
That's right. It functions pretty much like an app store you'd find on your phone or your desktop computer. It provides these pre-built, fully validated, accelerated applications.
What kind of apps are we talking about?
We're talking quite complex stacks. Things like ready-to-run DPU PYNQ environments, that's Python productivity on Zinc with the DPU integrated, or dedicated smart camera application pipelines, maybe optimized for specific tasks like people counting or defect detection, or even complete robotics stacks pre-integrated with ROS2.
And these are free to try out?
Yeah, typically free for evaluation on the starter kits. And then, importantly, they are directly deployable onto the production SOMs when you're ready to build your product.
Okay, so you find an app, you try it, you like it, you deploy it, and the deployment process itself. Does that also feel like software?
That's the goal. The applications are packaged using standard Linux deployment frameworks. Think Debian packages or similar. This allows for easy, secure, over-the-air OTA installation and updates.
Just like managing software packages on any modern server or desktop OS?
Exactly. Apt install my accelerated app, basically. And this whole approach is built on what they call a non-negotiable Linux-first strategy.
Meaning strong support for standard Linux distributions.
Right. Robust support for popular choices like Ubuntu long-term support, LTS releases, or embedded build systems like Linux from AMD Xilinx, and the vendor-neutral Yocto project.
Which ensures a familiar, stable environment for developers using Python, C++, Air, and especially frameworks like ROS2 in the robotics space.
Precisely. This is the mechanism designed to minimize that learning curve we talked about, to provide immediate, tangible value for software teams looking to adopt adaptive hardware without a huge upfront investment in retraining or specialized tools. Hashtag 4.2 on-target utilities for dynamic reconfiguration.
Okay, the App Store makes it easy to get started with pre-built accelerated functions. But the real magic of adaptive hardware, of FPGAs, is its ability to change its function after deployment, right? Dynamically reconfiguring the hardware.
That's one of the most powerful capabilities, yes. The ability to change the hardware's personality mid-mission.
So imagine you've shipped a product running one specific AI algorithm. A year later, a much better algorithm comes out. You don't want to do a hardware recall.
Absolutely not. Or maybe the device's mission changes dynamically. It needs to switch from, say, a surveillance mode to a high-speed inspection mode. You need to reconfigure the FPGA fabric, the PL, at runtime.
And critically, you need to do this without requiring a full system reboot, right? That would be unacceptable for anything needing high uptime, like medical gear or factory controllers.
Exactly. Downtime is often not an option. So Kria provides specialized utilities that run on the target device to manage this flexibility. This whole concept is often called dynamic function exchange, or DFX.
Okay, DFX. And there are specific tools provided for this. You mentioned XMutel.
Right. XMutil is kind of the user-facing command line tool, often wrapped in Python. It acts as the intelligent front end for managing these hardware configurations.
What does it do?
When you run it, it first queries the hardware. It identifies the specific Kria SOM model and, importantly, the carrier card it's currently plugged into, usually by reading an onboard EEPROM chip.
Ah, so it knows the exact hardware platform.
Yes. And based on that, it can then filter the available accelerated applications or hardware configurations, often called overlays or shells, from the App Store or local storage, ensuring compatibility. For example, it might only show you packages specifically designed for your KV260 Vision Kit platform. It's the user's interface to initiating a hardware change.
Okay, so XMutil is the front door. What's doing the actual heavy lifting underneath? You mentioned DFX NGR.
Yes, DFX-NGR, which stands for Dynamic Function Exchange Manager. This is the underlying AMD library, and typically an on-target daemon, a background service. It handles the low-level mechanics of loading and unloading the hardware configuration files.
These are the bitstream files.
Exactly, the actual files that define the hardware circuit, usually ending in .bit.bin or similar. So let's take your drone example. Maybe it boots up running a thermal vision algorithm defined by bitstream A.
Okay.
Mid-flight, the mission changes. Maybe it needs to switch to a high-resolution optical flow algorithm for obstacle avoidance defined by bitstream B. The characterismal tool would trigger the change, and the DFX-NGR daemon would then securely unload bitstream A from a designated region of the PL fabric and load bitstream B into that same region.
All while the main Linux OS keeps running on the ARM cores.
Correct, without interrupting the running kernel or rebooting the device. That capability to functionally adapt to the hardware at runtime is the core promise of DFX, and these tools make it accessible from a software level. Hashtag 4.3 advanced customization flows.
So Kria does a great job, it seems, of shielding the mainstream software developer from that deep hardware complexity using the App Store and DFX tools. But what about the hardcore embedded systems engineers? The ones who do need to customize the hardware down to the register level or integrate their own proprietary sensor interfaces or really optimize things. Kria can't just ignore them, can it?
Absolutely not, and they don't. While the low-code, app-based approach is heavily emphasized for broadening adoption, deep hardware customization is still fully supported through the more traditional AMD Xilinx tool flows.
Primarily using the Vetus tool suite.
Yes, the Vetus Unified Software Platform is the preferred environment for that kind of custom hardware-software co-design.
Can you walk us through, maybe briefly, what that Vetus flow looks like in the Kria context? What are the key steps and outputs if you're building a custom accelerator?
Sure. It typically starts in the Vivado design suite. That's the traditional hardware design environment. Here, you define your custom hardware structure, maybe integrating your own IP blocks alongside AMD's IP, like the DPU. This process generates a static hardware definition file, usually in .exe file.
Okay, the hardware blueprint.
Right. Then you move into Vitus. Vitus takes that hardware blueprint, .xsa, and compiles your custom accelerator code, which you might write in C++ AC or OpenCL, into the actual hardware binary that runs on the PL. This output is often called the .xcl bin file.
The executable for the FPGA fabric.
Exactly. But crucially, alongside the .xcl bin, Vitus also generates another critical piece, the device tree overlay, or .dtbo file.
Ah, the device tree overlay. Why is that .dtbo file so important? What does it do?
The .tbbo file is essentially the communication bridge between your newly created custom hardware in the PL and the Linux operating system running on the PS, the ARM cores.
It tells Linux about the new hardware.
Precisely. It informs the Linux kernel about the hardware that just got instantiated in the programmable logic. It tells the OS things like, what is this new peripheral? Where does it live in the system's memory map? What interrupts does it use? How should the host application drivers communicate with it?
So it allows Linux to see and manage the custom hardware using standard driver mechanisms.
Exactly. It allows developers to create highly custom hardware IP, yet still interact with it from their software applications using familiar Linux device driver interfaces, like dev nodes or standard APIs. It keeps the software interaction relatively standard, even if the underlying hardware is bespoke.
And for engineers who need a really lean, optimized OS, not a full Ubuntu desktop.
They still have options too. Traditional embedded engineers can use tools like Petalinux or the Yocto project to build highly customized, minimal Linux system images, stripping out everything unnecessary for their specific application, making it smaller, faster booting, and potentially more secure than a general purpose distribution. So deep customization is definitely still on the tag, tag 4.4, application-specific frameworks, and ecosystem.
Okay, so you have the low-code path via the App Store and the high customization path via Vitis. To really drive adoption in specific high-growth industries, it seems like AMD has also developed some domain-specific software stacks that build on top of this foundation. The Kria Robotics Stack, KRS, sounds like a prime example for the robotics market.
Yeah, the KRS is a really important piece for the KR260 robotics starter kit and the broader robotics push. It provides deep optimized integration with ROS2.
ROS2 being the robot operating system, the standard framework for robotics development these days.
Exactly. So KRS allows robotics engineers who are already comfortable working within the ROS2 ecosystem, using concepts like nodes, topics, services, to easily offload computationally intensive parts of their robotic application.
Like what kind of tasks?
Things that often bottleneck the CPU in a robot. Perception tasks like processing LiDAR point clouds or running complex visual SLAM, simultaneous localization and mapping algorithms, path planning computations, or even real-time high-frequency control loops for manipulators. These can be pushed from standard ROS2 nodes running on the CPU into accelerated hardware blocks running in the PL fabric.
Freeing up the CPU and getting deterministic performance from the hardware.
That's the goal. We see the payoff in example projects like those autonomous robotic riding arms you mentioned, where they need extremely high-performance computation for sub-millisecond deterministic control to draw accurately. The KRS provides the hooks to make that acceleration seamless within a standard ROS2 workflow.
And similarly, for the industrial control space, especially with the K24 SOM, there's the Vitis Motor Control Library.
Yes, another example of a domain-specific library. This one aims to speed up development for control systems architects who often work with tools like Python for scripting or MATLAB and Simulink for modeling and simulation.
So they can prototype complex motor control algorithms.
Right, things like field-oriented control, FOC for high-efficiency motors. They can prototype these algorithms in familiar software environments and then use the library to quickly push the computationally intensive parts into hardware acceleration on the K24's PL, often without needing to write any VHDL or Verilog themselves. It speeds up that iteration loop significantly.
Okay. And finally, let's touch on a partner ecosystem again. You mentioned it earlier. This seems vital for bridging the gap, especially for software-focused companies that adopt Kria but might lack that deep in-house FPGA expertise for customization.
Absolutely critical. AMD clearly recognizes they can't do it all themselves. They foster a partner ecosystem companies that provide essential design services, specialized IP cores.
What kind of specialized IP?
Could be anything. Maybe pre-built, highly optimized pipelines for specific types of image sensors in machine vision, or IP for specific industrial communication protocols, or maybe alternative AML acceleration IP tailored for niche algorithms where the standard DPU isn't the perfect fit.
So these partners help fill the gaps.
Exactly. They ensure that even users who are primarily software-centric can still achieve turnkey productization. They can leverage these third-party experts to handle the deep hardware customization details when needed, further accelerating their path to market and reducing risk. It completes that picture of democratizing adaptive hardware by providing multiple levels of support. Okay, so we've covered the tech, the architecture, the software. Now let's connect all of that capability and accessibility back to the bigger business picture. Because honestly, the financial savings story here might be the most compelling part.
You mentioned earlier it's not just about the unit price of the chip inside the SOM.
No, definitely not. The critical metric, especially for businesses making investment decisions, is the total cost of ownership, the TCO, considered across the entire product lifecycle. Hashtag point one, quantifying non-recurring engineering injury savings.
And the biggest chunk of that TCO saving with the SOM approach seems to come from slashing those non-recurring engineering costs, the NRE. especially for OEMs building products in low to mid volumes.
Absolutely. Using the SOM fundamentally eliminates the need for the OEM's internal teams to design the most difficult, expensive, and risky parts of the system. We're talking about routing the MPSE itself, laying out the high-speed DDR memory interfaces, designing the complex multi-rail power trees.
All the stuff that requires specialized expertise and tools.
Exactly, and all the debugging and validation that goes with it. Our sources and AMD's own materials consistently estimate that just bypassing this core digital design phase alone, it can save an OEM somewhere in the ballpark of $250,000 in NRE effort.
$250,000. Where does that number come from? Let's break that down a bit.
Well, think about what goes into a custom chip-down design for something like this. You're paying for months, maybe many months, of highly specialized, expensive hardware engineer time people who are experts in high-speed signal integrity.
Not cheap resources.
Not at all. You're paying for licenses for those very expensive EDA simulation tools, which can run tens or even hundreds of thousands of dollars per year per seat. You're paying for multiple iterations of PCB fabrication and assembly. Each board spin costs money and takes time.
Prototype builds, yeah.
And often, especially with complex DDR layouts, you might even need to bring in external third-party signal integrity consultants to review and validate your design. That adds up incredibly quickly. The SOM basically lets you skip almost all of that.
Wow. And the savings don't necessarily stop at the design phase, right? They can extend into manufacturing and QA too.
They often do. Since those high-density BGA components, particularly the main MPSoC and the DDR chips, are mounted and validated on the SOM by the vendor.
Who has specialized equipment and processes.
Right. The OEM often avoids the need for expensive and time-consuming post-assembly inspection processes for that core subsystem on their own production line. Things like BGA X-ray inspection to check for soldering defects under the chip. You essentially get guaranteed BGA integrity for the hardest part of the system because the vendor managed it.
That simplifies incoming QA and potentially improves final product yield. And we shouldn't forget regulatory compliance either. That can be a huge hidden NRE cost and time sink.
Oh, massive. Getting products certified for sale in different regions, things like CE marking in Europe, FCC in the US, UL for safety, it's an incredibly complex, expensive, and time-consuming process.
Which requires specialized testing labs, lots of documentation.
Exactly. Each certification can individually cost tens of thousands of dollars per region and often involves multiple rounds of testing and paperwork. Using a pre-certified module in Kria SMs often come with major regional certifications already completed or inherited, significantly simplifies the OEM's path to getting their final product certified. It can dramatically reduce both the direct cost and the complexity, potentially shaving months off that final compliance cycle.
Okay, those NRE savings are huge, easily quantifiable. But maybe even more important, from a strategic business perspective, is the impact on time to market, the TTM.
This is often the decisive factor, especially in fast-moving tech markets. The claim here is pretty bold. Using a Kria SM can potentially reduce the overall product development and deployment time by up to 9 months compared to starting a traditional chip-down design from scratch.
9 months. That's nearly a full year shaved off the development cycle. How is that even possible? Where do those savings come from?
It comes from bypassing the most volatile, unpredictable, and often delay-prone phases of hardware product development. You skip the potentially lengthy iterative cycles of custom PCB design, fabrication, and assembly. You skip the often painful and complex initial hardware bring-up, debugging, just getting the processor to boot correctly, getting the DDR memory stable.
The does it even turn on phase.
Exactly. And you skip the painstaking, low-level process of initial bootloader development and base kernel driver integration for all the core peripherals. When you start your project with a SOM, you're typically starting with a fully tested, debugged, bootable system right out of the box. You jump months ahead in the development schedule, effectively starting at what might have been month 6 or 7 of a chip-down project.
That is a massive head start. And from a strategic business viewpoint, that 9-month TTM advantage, it often holds far greater financial value than just saving a few dollars on the per-unit material cost, doesn't it?
Absolutely. Think about what getting your product to market 9 months faster means. It allows for rapid market capture, being first or second with a new capability. It helps establish crucial intellectual property and brand leadership. It means you start generating revenue 9 months earlier, while your competitors might still be debugging their first prototype boards.
Especially in hot sectors like AI or robotics, where the landscape changes so quickly.
Exactly. In those fast-moving sectors, being first or second to market often determines who captures the lion's share of of the early adopter revenue and market momentum. So the SOM isn't just about saving NRE money, it's about gaining a potentially overwhelming competitive time advantage and significantly minimizing strategic market risk. Hashtag tag 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 5.3, the TCO break of analysis.
Okay, so we have NRE savings, we have TTM advantage, but we do need to address the common counter-argument, the assumption that often gets made. Well, the naked MPSoC chip itself costs less than the complete SO module. So surely if I'm building enough units, doing a custom chip-down design must be cheaper in the long run.
That is the classic and often flawed line of reasoning. It's flawed because it completely fails to properly amortize those significant NRE expenses we just detailed over the actual production volume.
It ignores the upfront investment.
Exactly. Look, if you are genuinely building a product that requires millions of units per year, consistently, over its entire lifetime, think maybe a mainstream smartphone component, then yes, at some extremely high volume point, the marginal per unit cost saving of designing everything yourself might eventually outweigh the massive upfront NRE.
But Kria isn't really targeting that multi-million unit market, is it?
No, the Kria SO approach seems explicitly designed for and most compelling in the sweet spot, low to mid production volumes.
What kind of volumes are we talking about roughly?
Maybe in the range of hundreds up to perhaps tens of thousands of units per year. For products in that volume range, the SOM approach is almost unequivocally more cost-effective from a TCO perspective. Why? Because those prohibitive NRE costs of a custom design, that $250,000 plus ongoing support plus risk, simply cannot be spread thinly enough across that limited sales volume to make sense. The NRE per unit remains too high.
And you also have to consider the functional cost comparison, right? Not just the chip cost.
Absolutely critical point. The functional unit cost of the Kria SM, which includes not just the MPSoC, but the pre-tested board, the high-speed DDR memory, all the required power management ICs, clocking, basic storage, the connector, the thermal spreader.
Everything needed to make the chip actually work.
Right. That functional cost is estimated, as we said, to be somewhere between 2x and 10x cheaper than if an OEM were to buy just the naked MPSoC chip and then try to source, integrate, and validate all that equivalent supporting infrastructure themselves.
So the break-even point where chip down theoretically becomes financially superior, it's pushed out to very high volumes.
Yes, typically only reached at very high, sustained long-term annual volumes, likely well into the tens of thousands of units per year, or even more. And even then, the strategic benefits we discussed, the drastically reduced TTM, the mitigated development risk, the simplified supply chain often still weigh heavily in the SOM's favor, especially given how volatile supply chains and market demands have become.
Hashtag 5.4 supply chain and longevity.
That leads perfectly into the next point. Supply chain management, which has been a colossal headache for pretty much all OEMs globally over the last few years. How does using SOM help there?
It fundamentally shifts a significant portion of the supply chain burden and risk away from the OEM and onto the module vendor, in this case, AMD.
How so?
The module vendor assumes the primary responsibility for sourcing, managing inventory fluctuations, qualifying multiple suppliers, and critically mitigating end-of-life EOL risks for all those complex components on the SOM.
Like the specific DDR memory chips, the power ICs, the MPSoC itself? Exactly. These components, especially memory, can have relatively short market lifetimes or sudden allocation issues. If you've designed them into your custom board and your memory supplier suddenly issues an EOL notice or can't deliver,
you're scrambling. Potential line down, costly redesign.
big trouble. But if that memory chip is on the SOM you're buying, the OEM is largely shielded. It becomes the SOM vendor's problem to manage that transition, qualify an alternative, maybe rev the SOM slightly, and ensure continued supply and certification for their customers. It acts as a crucial risk mitigation buffer against supply chain volatility.
That's a huge relief for many companies, I imagine, and particularly for the industrial sector.
Yeah.
They don't just need supply, they need stability and longevity, right?
Yeah.
They deploy equipment expected to last 5, 10, 15 years.
They demand ironclad longevity support, and Kria addresses this. The SOMs are explicitly supported for long industrial life cycles. We saw the K24 Industrial SO, for example, is specified with 5 years of production availability, and often support extends beyond that. This provides the necessary stability and planning horizon for OEMs serving sectors like industrial automation, medical equipment, or critical infrastructure, where long deployment times and support guarantees are non-negotiable. Hashtag 6. Real-world application deep dive.
Okay, we've covered the technology, the software, the economics. Let's try to ground all this analysis now with some concrete examples. How does this adaptability and efficiency actually play out in real-world applications? Starting with the KV260 Vision AI Starter Kit and the K26 SOM, clearly targeted at vision applications.
Right, the K26 SOM is really optimized for high-performance edge vision tasks. Think smart cameras in retail or cities, advanced driver assistance systems, ADS, industrial machine vision for quality control, medical imaging.
And a good example might be a system needing to handle multiple camera streams at once.
Exactly. An exemplary use case highlighted in the source materials is an embedded vision platform built around the K26 that can manage inputs from up to 4 high-resolution cameras simultaneously.
And this again comes back to leveraging that programmable logic, the PL fabric, for more than just the AI inference.
Absolutely. The genius here is that the entire image sensor processor, ISP pipeline, handling tasks like demosaic the raw Bayer sensor data, noise reduction, color correction, lens distortion correction, that entire complex pipeline can be implemented directly and deterministically in the PL fabric.
Running in dedicated hardware logic next to the DPU.
Precisely. This ensures that high-quality, uncompressed image data is immediately available to the DPU with minimal latency. That dedicated, optimized pathway within the chip eliminates bottlenecks, preserves critical image details.
Which you might lose if you had to compress the video heavily to send it off chip for processing.
Exactly. And it yields really impressive performance per watt for the whole vision task, often quoted as better than 10 TOPS per watt specifically for vision pipelines. This is crucial for safety-critical applications like AD or robotics, where any image distortion, motion blur, or added latency is simply unacceptable.
Okay. That makes sense for vision. Now, shifting to the KR260 robotics starter kit and the K24, K26 SAMs in robotics and deterministic control applications.
Yeah, this is another sweet spot. The Kria robotics stack, KRS, which we mentioned, is key here. By integrating tightly with ROS2, it makes it much easier for robotics engineers.
Easier to do what specifically?
Easier to identify the computationally intensive bottlenecks in their ROS2 application, often things like sensor fusion, perception algorithms like object detection or SLAM, motion planning, or those fine-grained control loops, and then offload those specific ROS2 nodes or processing graphs directly into accelerated hardware functions running in the PL.
So the CPU handles the high-level ROS coordination, the hardware handles the heavy lifting.
That's the idea. This hardware-software partitioning is vital for applications like those autonomous robotic arms we discussed, or mobile robots navigating complex environments. They require that real-time, high-frequency, deterministic control that the PL fabric excels at providing, ensuring the robot operates accurately, smoothly, and safely.
And speaking of determinism, that customizable PL fabric is also essential for handling specialized industrial networking protocols, right? Things that standard Ethernet chips often struggle with.
This is a massive application area, particularly for the K24 SOM with its focus on industrial control. Standard Ethernet is typically best effort, but industrial automation demands guaranteed timing, often down to the microsecond level.
Protocols like EtherCAT, Profinet.
Exactly. Time-sensitive networking, TSN, EtherCAT, Profinet, ART, Ethernet up with CIP sync, these protocols have very strict timing requirements. The programmable nature of the Kria PL allows OEMs to implement the necessary hardware logic, the custom MAC controllers, the precise time-stamping mechanisms directly on the SOM to support these deterministic industrial Ethernet standards natively.
So the SRM can act as a powerful industrial communication gateway.
Precisely. And crucially, it often allows the OEM to consolidate both the time-critical control traffic and general IT management data onto a single common Ethernet network infrastructure. This simplifies the overall factory or machine network architecture, reduces wiring, and potentially lowers costs by reducing the number of specialized external interface chips required. It's integration and acceleration combined.
Okay. And just to close the loop, if an OEM runs into a really niche requirement within these applications, say a custom filter needed for a very specific low-light camera sensor or a unique motor encoder interface, that partner ecosystem we talked about provides the fallback.
Exactly. It ensures that even if the need is highly specialized, the software-centric adopter doesn't necessarily get stuck trying to become a deep FPGA expert overnight. They can engage with partners who provide that specific IP core or the necessary design services to integrate it onto the Kria SOM. It completes the picture, providing an escalator of options from off-the-shelf apps to full customization with support available at each step. Hashtag, outro.
Okay, let's try and synthesize all of this. We've covered a lot of ground. To recap the core findings for you, our listener, Kria really represents a major, very calculated strategic pivot by AMD, It's aimed squarely at democratizing adaptive hardware, making FPGAs accessible beyond the traditional experts.
And its value proposition is really dual, isn't it? And incredibly powerful when you combine them. Architecturally, you get impressive efficiency, high TOPS per watt for AI and other tasks, largely thanks to that configurable DPU working tightly with other custom processing pipelines built in the PL fabric.
Holistic acceleration.
Holistic acceleration, yes. And then strategically, perhaps even more impactfully, the value lies in that potentially overwhelming reduction in total cost of ownership.
Right. By shifting potentially hundreds of thousands of dollars in NRE costs, reducing significant technical risk, and slashing maybe up to 9 months of time-to-market risk, shifting all that away from the OEM and onto the module vendor.
The Kria SOM approach can justify its unit cost premium many, many times over, especially for those low to mid-volume projects.
And the key enabler, the thing that really unlocks this for a broader audience, is that low-code, Linux-first software ecosystem. The App Store providing pre-built solutions, the Xmutal and DFX NGR tools allowing dynamic updates. That's the essential mechanism removing the traditional barrier of entry for software and AI developers.
Making it faster and less risky to get products launched in those high-growth sectors like vision AI and robotics, where, frankly, being first or fastest often matters most. This really raises an important question as we wrap up.
Go on. If a pre-validated, dynamically reconfigurable hardware module, backed by a modern software stack and ecosystem, can realistically save you 9 months of critical development time, eliminate maybe $250,000 or more in upfront engineering costs, and mitigate significant supply chain risk. At what point does clinging to the idea of saving just a few dollars on the raw chip price by doing a full custom design become, well, an unforgivable strategic mistake? A mistake that actually costs you market share, time, and ultimately far, far more money in the long run.